The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so let's begin. Today I'm going to review linear algebra. So I'm assuming that you already took some linear algebra course, and I'm going to just review the relevant concepts that will appear again and again throughout the course. But do interrupt me if some concepts are not clear, if you don't remember some concept from linear algebra. I hope you do, but yeah, please let me know. I just don't know. You have very different level of, you have very different background knowledge. So it's hard to tune to one special group. So I tailored this lecture notes so that it's a review for those who took the most basic linear algebra course. Yeah. So if you already have that experience and don't understand it, please feel free to interrupt me. Okay. So I want to start by talking about matrices. A matrix, in a very simple form, is just a collection of numbers. For example, 1, 2, 3, 2, 3, 4, 4, 5, I don't know, 10. You can pick any number of rows, any number of columns. You just write down numbers in a square format, and that's a matrix. What's special about it? And so what kind of data can you arrange in a matrix? So I'll take an example which looks relevant to us. So for example, we can index the rows by stocks or companies like Apple. I don't know, Morgan Stanley should be there. What else? Google. And then maybe we can index a column by dates. So I'll say July 1st, October 1st, September 1st. And the numbers, you can pick whatever data you want, but probably the sensible data will be the stock price on that day. I don't know, for example, 400, 500, and 5,000. That would be great. So these kind of data, that's just the matrix. Okay? So defining a matrix is really simple, but why is it so powerful? So that's an application point of view, just as a collection of data. But from a theoretical point of view, a matrix, an m by n matrix, is an operator. It defines a linear transformation. A defines a linear transformation from the vector space, n-dimensional vector space, to the m-dimensional vector space. That sounds a lot more abstract than this, right? Okay, so for example, let's just take a very small example. If A is a 2 by 2 matrix, 2, 0, 0, 3, then 2, 0, 0, 3 times, let's say, 1, 1 is just 2, 3. Right? Okay. Does that make sense? It's just matrix multiplication. So now try to combine the point of view. What does it mean to have a linear transformation defined by a data set? Okay? And things start to get confusing. What is it? Why does a data set define a linear transformation? And does it have any sensible meaning? Okay, so that's a good question to have in mind today. And try to remember this question, because today I will try to really develop a theory of eigenvalues and eigenvectors in a purely theoretical language. But it can still be applied to these data sets and give very important properties and very important, quantities. You can get just some useful information out of it. Try to make sense out of why it happens. Okay? So that will be the goal today. So really treat linear algebra as a theoretical thing, but remember that there's some data set, like really data set underlying. Okay, this doesn't go up. That was a bad choice for my first board. Oops, sorry. Okay. So the most important concepts for us are the eigenvalues and eigenvectors of a matrix, which is defined as a real number lambda and a vector v is an eigenvalue and eigenvector of a matrix A if A times V equals lambda times V. Okay? We also say that V is an eigenvector corresponding to lambda. So remember, eigenvalues and eigenvectors always come in pairs. And they are defined by the property that A times V is equal to lambda times V. Okay. First question, does all matrix have eigenvalues and eigenvectors? No? So, okay, I'll read. It looks like this is a very strange equation to satisfy, but if you change it in this form, A minus lambda I V equals 0, it still looks strange. But at least you understand that, oh, it's if and only if. This can happen only if. This can happen, happens only if A minus lambda I does not have full rank. So determinant of A minus lambda I is equal to 0. If and only if, in fact. Okay. So now comes a very interesting observation. Determinant of A minus lambda I is a polynomial of degree n. Okay, I made a mistake. I should have said this is only for n by n matrices. This is only for square matrices, sorry. It's a polynomial of degree n. That means it has a solution. Has to give n in terms of lambda. So has a solution. It might be a complex number. I'm really sorry. I'm nervous in front of the video. It's a complex. I understand why you were saying that it doesn't necessarily exist. But let me repeat. I made a few mistakes here, so let me repeat here. For n by n matrix A, a complex number lambda and a vector v is an eigenvalue and eigenvector if it satisfies this condition. It doesn't have to be real. Sorry about that. And now if we phrase it this way, because this is a polynomial, it always has at least one solution. Okay? That was just a side point. Very theoretical. So we see that there always exists at least one eigenvalue and eigenvector. Now we saw its existence. So what is the geometrical meaning of it? Okay, now let's go back to the linear transformation point of view. So suppose A is a 3 by 3 matrix. Then A takes a vector in R3 and transforms it into to another vector in R3. But if you have this relation, what's going to happen is A, when applied to V, it will just scale the vector V. So if this was the original V, A of V will just be lambda times this vector. That will be our A of V, which is equal to lambda of V. So eigenvectors are those special vectors which, when applied this linear transformation, just get scaled by some amount, where that amount is exactly lambda. So what we established so far, what we recall so far, is every n by n matrix has at least one such direction. There is some vector where the linear transformation defined by A just scales that vector, which is quite interesting. If you've never thought about it before, there's no reason such vector should exist. Of course, I'm lying a little bit because these might be complex vectors, but at least in the complex world, it's true. So if you think about this, this is very helpful. It gives you these vectors, from these vectors' point of view, this linear transformation is really easy to understand. Okay? That's why eigenvalues and eigenvectors are so good. It breaks down the linear transformation into really simple operations. So let me formalize that a little bit more. So in an extreme case, a matrix, an n by n matrix, A, we call it diagonalizable if there exists an orthonormal matrix. I'll recall what that is. U such that A is equal to U times D times U inverse for a diagonal matrix D. Okay, so let me iterate through this a little bit. What is an orthonormal matrix? It's a matrix defined by the relation U times U transpose is equal to the identity. What is a diagonal matrix? It's a matrix whose non-zero entries are all on the diagonal. All rest are 0. Okay. Why is it so good to have this decomposition? What does it mean to have an orthonormal matrix like this? It means, basically, I'll just explain what's happening. If that happens, if a matrix is diagonalizable, if this A is diagonalizable, there will be 3 directions, B1, B2, B3, such that when you apply this A, B1 scales by some lambda 1, B2 scales by some lambda 2, and B3 scales by some lambda 3. So you can completely understand the transformation A just in terms of these 3 vectors. Okay? Okay. So the stuff here will be the most important things you'll use in linear algebra throughout this course. So let me repeat it really slowly. Okay, so an eigenvalue and eigenvector is defined by this relation. We know that there are at least one eigenvalue for each matrix, and there is an eigenvector corresponding to it. And eigenvectors have this geometrical meaning, where vector is an eigenvector if the linear transformation defined by A just scales that vector. So for our setting, the real good matrices are the matrices which can be broken down into these directions. And those directions are defined by this U, and D defines how much it will scale. So in this case, U will be our v1, v2, v3. And D will be our lambda 1, lambda 2, lambda 3, all 0. Okay. Any questions so far? Okay, so that is abstract. Now remember the question I posed in the beginning. So remember that matrix where we had stocks and dates and stock prices and the entries? What will an eigenvector of that matrix mean? What will an eigenvalue mean? Okay. So try to think about that question. It's not like it will have some physical counterpart, but there's some really interesting thing going on there. Okay. Okay. The bad news is that not all matrices are diagonalizable. Okay? If a matrix is diagonalizable, it's really easy to understand what it does, because it really breaks down into these 3 directions. If it's a 3 by 3, it's an n by n, it breaks down into n directions. Unfortunately, not all matrices are diagonalizable. But there is a very special class of matrices which are always diagonalizable. And fortunately, we will see those matrices throughout the course. Most of the matrices, n by n matrices we will study, fall into this category. So an n by n matrix, A is symmetric if A is equal to A transpose. Okay, before proceeding, please raise your hand if you're familiar with all the concepts so far. Okay, good. Get a good feeling. Okay, so a matrix is symmetric if it's equal to its transpose. A transpose is obtained by taking the mirror image across the diagonal. Okay. And then it is known that all symmetric matrices are diagonalized. I made another mistake. Orthonormally. So this, I missed matrices orthonormally diagonalizable. So it's diagonalizable if we drop this condition, okay, and replace it with an invertible. Okay, so symmetric matrices are really good. And fortunately, most of the n by n matrices that we will study are symmetric. Just by the nature of it, it will be symmetric. The one I gave as an example is not symmetric. It's not symmetric, but I will address that issue in a minute. And another important thing is symmetric matrices have real eigenvalues. So really, this geometrical picture, for symmetric matrices, this picture is really the picture you should have in mind. Okay, so proof of theorem 2. Suppose lambda is an eigenvalue with eigenvector v. then, by definition, we have this. Okay. Now, multiply V transpose on both sides. It is lambda times the norm V. Okay. Now take the complex conjugate. Real symmetrical. Then, first take conjugate, we have V, AT, VT, ATV, and then take the conjugate of it. And we get lambda V. Okay. And this side is equal to VT, A, V. But because A is real symmetric, we see that A is equal to the conjugate, complex conjugate of A. So this expression and this expression is the same. The right-hand side should also be the same. That means lambda is equal to the conjugate of lambda. So lambda has to be a real. So theorem 1 is a little bit more complicated, and it involves more advanced concepts like basis and linear subspace and so on. And those concepts are not really important for this class, so I'll just skip the proof. But it's really important to remember these two theorems. Whenever you see a symmetric matrix, you should really feel like you have control on it, because you can diagonalize it. And moreover, all eigenvalues are real, and you have really good control on symmetric matrices. Okay, that's good. That was when everything went well. We can diagonalize it. So far we saw that if for a symmetric matrix we can diagonalize it, it's really easy to understand. But what about general matrices? In general, not all matrices are diagonalizable, first of all. So but sometimes we still want a decomposition like this. So diagonalization was A equals U times D times U transpose, or U inverse. But we want something similar. We want to understand, so our goal, want to still understand the matrix, given matrix A, through simple operations, such as scaling. When the matrix was a diagonalizable matrix, this was done. This was possible. Unfortunately, it's not always diagonalizable. So we have to do something else. But yeah, so that's what I want to talk about. And luckily, the good news is there is a nice tool we can use for all matrices, even though it's slightly weaker. In fact, a little bit more weaker than this diagonalization, but still, it distills some very important information of the matrix. So it's called singular value decomposition. So this will be our second tool of understanding matrices. It's very similar to this diagonalization, or in other words, I call this eigenvalue decomposition. But it has a slightly different form. So what is its form? So a theorem. Let A be an m by n matrix. Then there always exists U orthonormal matrices U and V such that A is equal to U times sigma times V transpose for some diagonal matrix. Let me parse through this theorem a little bit more. Whenever you're given a matrix, it doesn't even have to be a square matrix anymore. It can be non-symmetric. So whenever you're given an m by n matrix in general, there always exist two matrices, U and V, which are orthonormal, such that A can be decomposed as U times sigma times V transpose, where sigma is a diagonal matrix. But now the size of the matrix are important, so U is an m by m matrix, sigma is an m by n matrix, and V is an n by n matrix. That just denotes the size, dimensions of the matrix. Okay. So what does it mean for an m by n matrix to be diagonal? It just means the same thing. So only the II entries are allowed to be non-zero. So that was just a bunch of words. So let me phrase this. Decomposition, that part. Okay, so let me compare now eigenvalue decomposition with singular value decomposition. So this is EVD, what we just saw before. It only SVD. This only works for m by n matrices, which are diagonalizable. SVD works for all general m by n matrices. However, this is powerful because it gives you one frame, so V1, let's say V2, V3, for which A acts as a scaling operator. And like that. A, that's what A does, A does, A does. Okay. That's because these U on the both sides are equal. However, for singular value decomposition, this is called singular value decomposition. I just erased it. What you have instead is, first of all, the spaces are different. You take a vector in R to the m and bring it to R to the n by this operation A. What's going to happen here is there will be one frame in here and one frame in here. So there will be vectors V1, V2, V3, I don't know, V4, like this. And there will be vectors U1, U2, U3, like this here. And what's going to happen is, when you take V1, A will take V1 to U1 and scale it a little bit, according to that diagonal. A will take V2 to U2, we'll scale it. A will take V3 to U3, scale it. Wait a minute, but for V4, we don't have U4. What's going to happen is this is just going to disappear. U4, when applied A, will disappear. Okay? So I know it's a very vague explanation, but this geometric picture, try to compare them. A diagonalization, eigenvalue decomposition, works within its frame. So it's very, very powerful. You just have some directions and you scale those directions. But the singular value decomposition, it's applicable to more general class of matrices, but it's rather more restricted. You have two frames, one for the original space, one for the target space. And what the linear transformation does is just sends one vector to another vector and scale it a little bit. Okay? Okay. So now is another good time to go back to that matrix in the very beginning. So remember that example where he had a vector of companies and dates, and the entry was stock prices. Okay. So if it's a n by n matrix, you can try to apply both eigenvalue decomposition and singular value decomposition. But what will be more sensible is singular value decomposition in this case. I won't explain why and what's happening here. Peter will probably, you will come to it later. But just try to do some imagining before listening what's really happening in real world. So try to use your own imagination, your own language to express, see what happens for this matrix, what this decomposition is doing. Okay? Just looks like totally nonsense. Why does this have even a geometry? Why does it define a linear transformation, and so on? It's just a beautiful theory which gives many useful information. I can't really emphasize really this is just universal, being used in all science, these eigenvalue decomposition and singular value decomposition. So not just for this course, but pretty much it's safe to say in every engineering you'll encounter one of the forms. Okay, so let me talk about the proof of the singular value decomposition, and I will show you an example of what singular value decomposition does for some example matrix, the matrix that I chose. The proof of singular value decomposition, which is interesting. It relies on eigenvalue decomposition. Okay, so given a matrix A, consider the eigenvalues of A times A transpose. Get it right? Oh, sorry, A transpose A. Okay. First observation, that's a symmetric matrix. So if you remember, it will have real eigenvalues, and it's diagonalizable. Okay. So A, T of A has eigenvalues lambda 1, lambda 2, up to it's an m by n matrix, so lambda n. And corresponding eigenvectors v1, v2 up to vn. Okay. And so for convenience, I will cut it at lambda r and assume all rest is 0. Okay. So there might be none which are 0. In that case, we use all the eigenvalues. But I only am interested in non-zero eigenvalues. So I will say up to lambda r, they're non-zero. Afterwards, 0. It's just a notational choice. And now I'm just going to make a claim that they're all positive. This part is kind of just believe me. So, yeah. Then if that's the case, we can rewrite the eigenvalues. Rewrite eigenvalues as sigma 1 square, sigma 2 square, to sigma r square, and 0. Okay. That was my first step. My second step, that was step 1. Step 2 is to define u of 1 as a times v1 over sigma 1, u of 2 as a times v2 over sigma 2, and u of r as a times v of r over sigma r. And then u times r plus 1 as up to u times m as complete the above into a basis. So for those who don't understand, just think of, we pick u1 up to ur first, and then arbitrarily pick the rest. And you'll see why I only care about the non-zero eigenvalues, because I have to divide by sigmas, the sigma values, and if it's 0, I can't do the division. So that's why I identified those which are not 0. And then we're done. Okay? So it doesn't look at all like we're done. But I'm going to let my u be this, u1, u2, up to u n. Oh, sorry, it has to be n. My v, I'll pick as v1, v2 up to vr, and then vr plus 1 up to vm. This again just complete into a basis. Now let's see what happens. Okay, so A times U transpose times B. That's why it's wrong. I have to do U times A times B transpose. So I was right. V is N, U is M. Wait a minute. Yes. So U times A times V transpose, yeah. That will be 1 U2 UM. A, V transpose will be V1 transpose, V2 transpose, V N transpose. stop something. Sorry. Oh, that's the form I want, right? Yeah. So I have to transpose U and B there. Okay. Sorry. Oh, yeah. So, thank you. Thank you for the correction. I know this looks different from that, but I mean, if you flip the definition, it will be the same. So I'll just not stop making mistakes. Yeah. You have a question? Yeah. So, yeah, thank you. Yeah, that now makes more sense. Okay, thank you very much. And then you're going to have U1 transpose up to UN transpose A times V, because of the definition of V, will be lambda 1 of V1. A times V2 will be lambda 2 of V2, up to lambda R of VR, and the rest will be 0. These all define the columns. Okay. Now, let's do a few computations. So U1t times lambda 1 B1. U1t and lambda 1 B1. When you take the dot product, what you're going to get is V1t A transpose of V1 lambda 1 t. I'm missing something. V1 sorry about that. This is not right. These are A's. Trying to find the eigenvalues and eigenvectors A transpose A. Yeah. One. Okay, then that's U1 transpose times sigma 1 times U1. So that will be 1. Sigma 1. Yeah. And then if you look at the second entry, U1 transpose times AB2, you get U1 transpose times sigma 2 of U2. But I claim that this is equal to 0. Okay. So why is that the case? U1 transpose is equal to V1 transpose A transpose over sigma 1. Then we have sigma 2. U2 is equal to A times V2 over sigma 2. Those two cancels. And we have V1t AT A V2 over sigma 1. But V1 and V2 are two different eigenvectors of this matrix. In the beginning, we can have an orthonormal decomposition of A transpose A. That means V1t times V2 times that has to be equal to 0, because that's an eigenvalue. We have V1t times lambda 2 V2 over sigma 1. So we have lambda 2 over sigma 1 times V1 transpose V2. These two are orthogonal, so we have 0. So if you do the computation, what you're going to have is sigma 1, sigma 2 on the diagonal, up to sigma r, and then 0, 0 rest, and 0, 0 rest. Okay, sorry for the confusion. Actually, the process is quite simple. I was just lost in the computation in the middle. So process is first look at A transpose A, find the eigenvalues and eigenvectors, and using those, they define the matrix V. And you can define the matrix U by applying A times V over sigma. Each of those will define the entries of U. the reason I wanted to go through this proof is because this gives you a process of finding a singular value decomposition. Okay? It was a little bit painful for me, but if you have a matrix, there's just the simple steps you can follow to find the singular value decomposition. Okay? So look at this matrix, find its eigenvalues and eigenvectors, just arrange it in the right way. Of course, the right way needs some practice to be done correctly. But once you do that, you just obtain a singular value decomposition. And really, I can't explain how powerful it is. You will only later see it in the course, how powerful this decomposition will be. And only then you will be more appreciate how good it is to have this decomposition and be able to compute it so simply. So let's try to do it by hand. Yes?
So when you complete the basis for the second space,
Mm-hmm.
you are U of R plus 1.
Yes.
So you do this randomly completely, or do you need?
It has to be orthogonal. Orthonormal. Yeah. Yeah. This should be orthonormal. These should be orthonormal. These also. And that's a good point because that can be annoying when you want to do it by hand. Actually, it's the decomposition. You have to do some Gram-Schmidt process or something like that. But yeah. When I mean by hand, I don't really mean by hand, other than when you're doing homework, because you can use a computer to do it. And in fact, if you use computer, there are much better algorithms than this that are known, which can do this a lot more quickly and more efficiently. Okay, so let's try to do it by hand. Okay, so let A be this matrix 3, 2, 2, 2, 3, -2. And we want to make the eigenvalue decomposition of this. Okay. A transpose A, we have to compute that, is 3, 2, 2, 3, 2. And you'll get 13, 12, 2, 12, 13, -2, 2, -2, 8. And let me just say that the eigenvalues are 0, 9, and 25. Okay? So in this algorithm, sigma 1 square will be 25, sigma 2 square will be 9, and sigma 3 square will be 0. So we can take sigma 1 to be 5, sigma 2 to be 3, sigma 3 to be 0. Okay. Now we have to find the corresponding eigenvectors to find the singular value decomposition. And I'll just do one just to remind you how to find an eigenvector. So A transpose A minus 25I is equal to subtract 25 from these entries. You're going to get -12, 12, 2, 12, -12, 2, 2, -12, 13. Okay. And then you have to find a vector which annihilates this matrix, and that will be, I can take one of those vectors to be just 1 over square root 2, 1 over square root 2, 0, after normalizing. Okay. And then just do it for other vectors. Yeah, you find V2 to be 1 over square root 18, negative 1 over square root 18, 4 over square root 18. Okay. Now then find V3 to be the one that annihilates this, but I'll just say it's x, y, z. This will not be important. I'll explain why it's not that important. Okay. Then our V, as written above, actually there it was transposed, so I will transpose it. It will be 1 over square root 2, 1 over square root 2, 0. V2 is that, so we can write 1 over square root 18, negative 1 over square root 18, 4 over square root 18. And here just write x, y. Okay. And u will be defined as u1 and u2, where u1 is a times v1 over sigma 1, u2 is a times v2 over sigma 2. So multiply a by this vector, divide by sigma 1 to get u. I already did the computation for you. It's going to be, and this is going to be yes. V1. Okay. So if you did the computation right in the beginning to get the eigenvalues, then 8ta minus 25i, this has to be, what is it? Has to not have full rank. So there has to be a vector v, which when multiplied by this gives 0, 0, 0 vector. And then you say ABC, you set it equal to 0, 0, 0. And just solves the system of linear equations. Okay, there will be several of them. For example, you could take 1, 1, 0 as well, but I just normalize it to be half norm 1. So there's a lot of work involved if you want to do it by hand, even though you can do it. You have to find eigenvalues, find eigenvectors. In this case, you have to find 3 of them, and then you have to do more work and more work. But it can be done. And we are done now. So now this decomposes A into U sigma V transformation. So U is given as 1 over square root 2, 1 over square root 2, 1 over square root 2, minus 1 over square root 2. Sigma was 5, 3, 0. And V is this. So V transpose is just transpose of that. I'll just write it like that, where V is that. Okay. So we have this decomposition. And so let me actually write it because I want to show you why x, y, z is not important. 1 over square root 2, 1 over square root 2, 0, 1 over square root 18, minus 1 over square root 18, square root 18, x, y, z. Okay. The reason I'm saying this is not important is because I can just drop, what did I do here? It has to be 2 by 3. I can just drop this column and drop this column together. Let's be that form. Drop this and drop this all together. Okay? So the message here is that the eigenvectors corresponding to eigenvalue 0 are not important. The only relevant ones are non-zero eigenvalues. So drop this and drop this. That will save you some computation. So let me state a different form of singular value decomposition. So this works in general. As a corollary, we get a simplified form of SPD. becomes equal to U times sigma times V transpose. And A was an m by n matrix. U is still an m by m matrix. But now sigma is also an m by m matrix. This only works when m is less than or equal to m. And V is an m by n matrix. Okay. So the proof is exactly the same. And the last step is just to drop the irrelevant information. Okay. So I will not write down why it works, but you can see if you go through it, you'll see that dropping this part just corresponds to exactly that information. So that's a reduced form. So let's see. In the beginning, we had A. I erased A. A was a 2 by 3 matrix in the beginning. And we obtained a decomposition into 2 by 2, 2 by 2, and 2 by 3 matrix. If we didn't delete this column and this row, we would have obtained a 2 by 2 times 2 by 3 times 3 by 3 matrix. But now we can simplify it by removing those. Okay. And it might not look that much different on this board because I just erased one row. But many matrices that you'll see in real application have a lot lower rank than the number of columns and rows. So if R is a lot more smaller than both M and N, then this part really it's not obvious here. But if M and N has a big gap here, really the number of rows, that number of columns that you're saving, it can be enormous. Okay. So to illustrate an example, look at this. Now look at the stock prices, where you have companies and dates. Previously, I just gave you an example of a 3 by 3 matrix, but it's more sensible to have dates, a lot more dates than companies. So let's say you recorded 365 days of a year, even though the market is not open all days, and just like 5 companies. If you did a decomposition like this, you'll have a 5 by 5, 5 by 365, 365 by 365 here. But now in the reduced form, you're saving a lot of space. Okay? So if you just look at the board, it doesn't look like it's so powerful, but in fact it is. So that's a reduced form. And that will be the form that you'll see most of the time, this reduced form. Okay. So I made a lot of mistakes today. I have one more topic, but it's totally irrelevant topic. So any questions before I move on to the next topic? Yes?
The eigenvectors that represent like a standard vectoring over criteria?
Can you press the button?
I think you hold the button in while you're talking instead of just including according to what you're asking.
Do the eigenvectors
Mm-hmm.
represent a steady vectoring over the mean of the properties?
Oh, so in this data, what it means, you're asking what the eigenvectors will mean over this data. It will give you some stocks that it will give you like the correlation. Okay, so each eigenvector will give you a group of companies that are correlated somehow. It measures their correlation with each other. So I don't have a very good explanation what its physical meaning is. Maybe you can give this a little bit more.
Possibly. We will get into this in later lectures, but in the singular value decomposition, what you want to think of is these orthonormal matrices are really defining a new basis, sort of an orthogonal basis. So you're taking the original coordinate system and then you're rotating it, and without changing or stretching or squeezing the data, or you're just rotating the axes. So an orthonormal matrix gives you the cosines of the new coordinate system with respect to the old one. And so the singular value decomposition then is simply sort of rotating the data into a different orientation, and the principle or the orthonormal basis that you're transforming to is essentially the coordinates of the original data in the transformed system. So as Chongbum was commenting, you're essentially looking at a representation of the original data points in a linearly transformed space, and the correlations between different stocks, say, is represented by how those points are oriented in the new transformed space.
So, yeah. You'll have to see real data to really make sense out of it. Yeah. But another way to think of it is where it comes from. So all this singular value decomposition, if you remember the proof, it comes from eigenvectors and eigenvalues of A transpose A. Now, if you look at A transpose A, or I'll just say it's A transpose A times A transpose. It's pretty much the same. If you look at A times A transpose, you're going to get an m by n matrix. Okay? And it will be indexed both by these companies. And the numbers here will represent how much the companies are related to each other, how much correlation they have between each other. So by looking at the eigenvectors of this matrix, you're looking at the correlation between these stock prices, let's say, these companies' stock prices. And that information is represented inside the singular value decomposition. But again, it's a lot better to understand if you have real numbers and real data, which you will have later. So please, yeah, be excited and wait. You're going to see some cool stuff. Okay, so that was all for eigenvalue decomposition and singular value decomposition. And the last thing I want to mention today is something called Perron-Frobenius Theorem. This one even looks a lot more theoretical than the ones I showed you. But surprisingly, a few years ago, Steve Ross, he's a faculty in the business school here, found a very interesting result called Steve Ross recovery theorem that makes use of this theorem. So makes use of Perron-Frobenius theorem that I will tell you today. Unfortunately, you will only see a lecture on Steve Ross recovery theorem toward the end of the semester. So I will try to recall what it is later. But since we're talking about linear algebra today, let me introduce the theorem. This is called Perron-Frobenius. And you really won't believe that it has any applications in finance because it just looks so theoretical. Okay, I'm just stating a really weak form. Weak form. Let A be a n by n symmetric matrix whose entries are all positive, with positive entries. Then, there are a few properties that they have. First, there exists an eigenvalue. There exists the largest eigenvalue, lambda 0, such that lambda is less than lambda 0. Well, that's true for all other. This statement is really easy for symmetric matrices. So forget about, you can drop symmetric, but I'm just stating it because I'm going to prove only for this weak case. Just think about the statement when it's not symmetric. So if you have an n by n matrix whose entries are all positive, then there exists an eigenvalue lambda 0, a real eigenvalue, such that the absolute value of all other eigenvalues are strictly smaller than this eigenvalue. So remember that if it's not a symmetric matrix, they can be complex values. This is saying that there's a unique eigenvalue which has largest absolute value. And moreover, it's a real number. Okay. Second part, there exists an eigenvector, positive eigenvector with positive entries corresponding to lambda 0. So the eigenvector corresponding to this lambda 0 has positive entries. And the third part is lambda 0 is an eigenvalue of multiplicity 1. For those who know what it is. So this really is a unique eigenvalue with a unique eigenvector which has positive entries, and it's larger, really larger than other eigenvalues. So from the mathematician point of view, this has many applications as probability theory. My main research area is combinatorics, discrete mathematics. It's also used in there. So from the theoretical point of view, this has been used in many contexts. It's not a standard theorem taught in linear algebra, so I don't think, probably most of you haven't seen it before, but it's a well-known result and with many uses, theoretical uses, but you also see one used in later, as I mentioned, in finance, which is quite surprising. Okay. So let me just give you some feeling of why it happens. I won't give you the full detail of the proof, but just a very brief description. Sketch. When A is symmetric. Just simple case. A is symmetric. In this case, this statement, okay, if you look at it, first of all, A has real eigenvalues. Okay. I'll say it's lambda 1, lambda 2, up to lambda n. And at some point, so I'll say up to lambda I is greater than 0. Afterward is smaller than 0. But there are some positive eigenvalues, there are some negative eigenvalues. So that's observation 1. Things are more easy to control because they're all real. The first statement says that, maybe I should have indexed it as lambda 0. I'll just call this lambda 0 as well. This lambda 0 is in fact larger in absolute value than lambda n. That's the content of the first bullet. So if they all have all positive entries, then the largest positive eigenvalue dominates the smallest negative eigenvalue. Yeah. So why is that the case? First of all, to see that, you have to go through different steps. So we go into observation 2. Lambda 1. So look at lambda 1. Lambda 1 has an eigenvector with positive entries. Why is that the case? That's because if you look at A times V equals lambda 1 times V. If V, let me state it this way. Lambda 0 is the maximum of all lambda. Lambda 0. Okay, that's not entirely correct. 1. So if you look at this, if V has non-positive entries, if it has a negative entry, if V has a negative entry, then flip it. Flip the sign. And in this way, obtain new vector V prime. Since A has positive entries, what we conclude is that A times V prime will be larger than A times V. You have to look, okay? Think about it, because it has positive entries, if it has some negative part somewhere, the magnitude will decrease. So if you flip the sign, it should increase the magnitude. And this cannot happen. This shouldn't happen. Should not happen. Okay? That's where the positive entries part is used. If you have positive entries, then yeah, it should have, the eigenvector should have positive entries as well. So I will not work through the details of the rest. I will post it on the lecture notes. But really, this theorem, in fact, can be stated in a lot more generality than this. I'm stating only a very weak form. It doesn't have to have all positive entries. It has to only be something called irreducible, which is a concept from probability theory, from Markov chains. But yeah, here we will only use it in this setting. So I will review it later before it's really being used. But just remember that how these positive entries kick into this kind of statement, where there is an eigenvalue, largest eigenvalue, why there has to be a vector, which is all positive entries. Those will all come into play later. So I think that's it for today. If you have any last minute questions. Okay, if not, I will see you on Thursday.